Today, we're going to talk about a really powerful idea in statistics. It's called maximum likelihood estimation, which sounds kind of complicated, but trust me, the idea behind it is super intuitive. It's all about how we can let our data tell us the truth about the world. So let's just jump right in with a simple question. Imagine you flip a coin 100 times, and you get 55 heads. Now, you know that a perfectly fair coin should give you something pretty close to 50 heads, right? So what's going on here? Is this just random chance? Or is this coin maybe a little bit biased? How do we even begin to decide what the real story is? And this little coin puzzle is actually a perfect example of a much bigger challenge we face all the time. We are literally swimming in data. Think about election polls, or how long a product is expected to last, or results from a medical trial. We can see all these outcomes, this data, but we don't know the hidden rules, the underlying process that actually created it. Our entire goal is to use the data we can see to make a really smart guess about the rules we can't. So how do we actually do that? How do we find those hidden rules? Well, it all comes down to a single, really elegant idea. We're going to find the best possible explanation for the data that we've already observed. This is where maximum likelihood estimation, or MLE for short, comes into play, and it all boils down to asking this one brilliant question. It kind of flicks the usual way we think about probability upside down. Instead of asking, hey, if my coin is fair, what's the chance I get 55 heads? MLE asks, okay, look, I already got 55 heads. That happened. Given that data, what kind of coin, what parameter, makes that outcome the most probable thing to have happened? It's a really powerful shift in thinking. And to answer that question, we need to get comfortable with this idea of likelihood. Now, that's a specific technical term. All it means is the probability of seeing our exact data, our 55 heads, if we assume a certain rule is true. So we're going to try on a bunch of different possible rules. We'll ask, what's the likelihood if the coin is fair? And what's the likelihood if the coin is biased this much? We're just trying to see which assumption makes our data look the least surprising. Now, this is a really crucial point, and it's where people can get a little tripped up. So let's be clear. Calculating the likelihood, the probability of the data given a rule, is not the same thing as asking for the probability of the rule itself. That second question is a whole other area of statistics called Bayesian statistics, which is awesome, but it's not what we're doing here. MLE keeps it simple. It just finds the rule that makes the data we're holding in our hands have the highest probability. All right, enough theory. Let's make this totally concrete. We're going back to our coin with its 55 heads, and we're going to see exactly how we can use this idea of likelihood to find the single best explanation. The process is wonderfully logical. First, we just pick a possible value for p. That's the coin's true hidden probability of landing heads. Then, we use a formula to calculate the likelihood of getting our 55 heads if that p were the real one. Then we just do it again. We try a different p and calculate its likelihood. We do this for a whole bunch of possible values for p. And finally, we just look at all our results and find the one p that gave us the absolute highest likelihood. That's our winner. So, for instance, if we test a p of 0.50, a perfectly fair coin, we get a certain likelihood. Okay. Then we test a p of 0.60, and we get another number. But as we try all the values in between, we see something amazing happen. The likelihood number goes up and up, it hits a peak, and then it starts to go down again. And where is that peak? It's right at a p of 0.55. That's our single best guess for the coin's bias. Now, of course, in real life, we don't have to sit there and test every single number by hand. That's what calculus is for. We can use math to find the exact top of that likelihood curve automatically. But honestly, the math just does the searching for us. The core idea is still incredibly simple. We're just finding the top of the hill. And the math gives us our answer. The maximum likelihood estimate for p is 0.55. And you'll see we put this little hat symbol over the p. That's just a way of saying that this is our best estimate based on the data we have. It's not necessarily the absolute final truth, but it's the most likely one. And this is where the pure beauty and intuition of MLE really shines through. The most likely probability of getting heads, given our data, turned out to be the exact fraction of heads we actually saw in our data. 55 heads out of 100 flips is 0.55. It just makes perfect sense. The parameter that makes our data the most probable is the one that perfectly mirrors our data. It's so elegant. And of course, this is for so much more than just coin flips. Maximum likelihood estimation is an absolute workhorse. It's used everywhere to solve all kinds of real-world puzzles, from manufacturing to ecology. Let's check out another example. Imagine a company that makes light bulbs wants to know how reliable they are. How could they figure out the average failure rate? So here's our setup. We'll start by assuming that bulb lifetimes follow a pattern called an exponential distribution. All you need to know is that this pattern is governed by a single parameter, called lambda, which represents the failure rate. So we test 5 bulbs. We let them run until they burn out and record how long they lasted. 2 years, 3, 1, 3, and 4 years. The average lifetime for this little sample is 2.6 years. So just like with the coin, we can build a likelihood function. We ask what value of lambda makes it most probable that we would see these 5 specific lifetimes. We use calculus to find the peak of that function, and it tells us our answer. The maximum likelihood estimate for the failure rate lambda is about 0.385. And check this out, that beautiful intuition pops up again. For this kind of distribution, the average lifetime is just 1 divided by the failure rate. And if you take 1 divided by our estimate of 0.385, you get 2.6 years, which is the exact average lifetime of the 5 bulbs we tested. Once again, MLE found the one parameter that makes our model perfectly reflect the sample we saw. Okay, let's do one more. This one's a classic. How in the world do ecologists figure out how many fish are in a lake? You can't just drain it and count them, right? Well, they use a clever method called capture-recapture. Here's how it works. They go out, catch 10 animals, put a little tag on them, and release them. Then they wait a while for them to mix back in. Then they go out again and catch a new sample of 20 animals, and in that new sample, they find that 4 of them have tags. So, what's our best guess for the total population? You guessed it, we build a likelihood function. We ask, what total population size would make our result, catching 4 tagged fish out of 20, the most probable outcome? We find the maximum, and it tells us our best estimate for the total population is 50. And the logic here is just so clean. If the total population is 50, then the proportion of tagged animals in the whole lake is 10 out of 50, which is 20%. And what proportion did we find in our sample? We found 4 tagged animals out of 20, which is also exactly 20%. The MLE found the one population size that makes our little sample a perfect miniature representation of the whole lake. So after flipping coins, testing light bulbs, and counting fish, let's just pull back and make sure we lock in this single biggest idea here. At its very heart, maximum likelihood estimation is just a principled, powerful method for being a good detective. It lets us take the clues we have, our data, and work backward to figure out the most plausible story of what happened. It helps us find that one hidden parameter, that one version of reality that makes our observations make the most sense. It's really a tool for finding the single best story that explains what we see. And it's used everywhere from finance to genetics. So the next time you see a statistic or a poll, just ask yourself, what's the hidden rule that would make this data the most likely? What story is this data trying to tell me?